before we start looking at all the awesome functions that are in algebra, let's just kind of start basic with relations and functions. And first of all, a relation is just any mapping of the elements of one set onto the elements of another set. So anytime that we're pairing up things with other things, it's going to be a relation. Now there's two parts to a relation, a domain and a range, because there's two sets that are being paired together. That first set is called the domain, and we might think of those as inputs or oftentimes as x's, the x values of an ordered pair. The range, on the other hand, is going to be the second set, the set that's being mapped onto, and those are the outputs, or in a lot of cases the y's. So we can represent relations in a lot of different ways. First of all, we could just look at it as a set of ordered pairs. Here we'll have the elements of the one set is all those x coordinates being paired with the elements of the other set, all the y coordinates. So we see that 1's paired with 2, 3 is paired with 4, and 5 is paired with 6. Another way we can look at it is as a table. If we just list out all the x coordinates and all of the y coordinates, first of all, it's easy to see what the domain is because it's all them x coordinates. And the range is easy too. It's 2, 4, 6, all those y coordinates. And we could also see how they're related to each other because 1 is paired with 2, 3 is paired with 4, and 5 is paired with 6 again, just by how they're lined up in a table. We could also look at the same relation as a graph, and because they are ordered pairs, we could just plot those ordered pairs. For instance, 1, 2 means we go to the right 1 and up 2. 3, 4 means we go to the right 3 and up 4. And then 5, 6, we go to the right 5 and up 6, which would be about right here. Now, I know your instinct is to say, okay, well, then that means we have a line. No, we don't, all right, because there's only 3 points in our relation. A line signifies infinitely many points because it says that we could have a point right here and a point right here. But those points are not part of our set, so we can't connect the dots. Our graph of this relation is just 3 points sitting on the plane. That's it, nothing else. The last one you probably haven't heard of before, but it's called a mapping diagram. With a mapping diagram, what we do is we put all the elements of the domain in one group. And then we put all the elements of the range in the other group, and we show how they're related with arrows. So 1 is related to 2, and 3 is paired up with 4, and 5 goes with 6. And so this shows the relation as well. So consider this set of 4 ordered pairs, -2, 3, -1, -1, 1, 3, and 2, -2. Can we represent this relation in those variety of different ways? And first of all, let's make a table out of it. When we make a table, we just go x and y. In the x, we just list the x coordinate, -2, and how it's paired with 3. So the next ordered pair is -1, -1. Then we go to 1, 3, and 2, -2. Pretty simple on how to represent a relation as a table. When it comes to the graph, all we need to do is plot the points again. So -2, 3 means we go to the left 2 and up 3. -1, -1 means to the left 1 and down 1. 1, 3 means to the right 1 and up 3. And 2, -2 means to the right 2 and down 2. Notice we don't connect any dots or anything. We just plot the points and that's it. The last one is mapping diagram. And when we list out the domain and range, one of the first things that you notice is that they're not the same size anymore, which probably doesn't make sense because we got 4 ordered pairs, so we got 4 x's and we got 4 y's. How come when I make my mapping diagram, I got 4 x's, but I only got 3 y's? And it goes back to our table. If we look at our table, we see this number 3 pops up a couple times. All right? Both times that 3 is a member of our range, but we don't have to list it both times. When we're talking about the range, we're just going to say all the numbers that are in there, not necessarily how many times that they're in there. How we show the relation will kind of point this out. First of all we got to do is draw them arrows. -2 is related to 3, so we draw an arrow down here to 3. In the next ordered pair, -1 is paired with -1, so we draw an arrow between those two. In this third ordered pair, -1 is paired with 3, so that's how we deal with that 3 popping up again, is we draw an arrow from 1 over to 3 again. Now we can see that those two different x values are both being related to that 3. And then lastly, 2 is related to -2. Through all this, it's pretty easy to see that the domain and the range are easy to find. The domain is going to be all them x values. Just look at your mapping diagram. They're going to be -2, -1, 1, and 2. Now, those are all the elements of the domain. The domain is a set, though, so we should put these braces around it to signify that it's a set. The range is -2, -1, and 3. Once again, we don't list that 3 again just because it's used twice. We only need to list it once. Those are all the elements. Let's make it a set by putting braces around it. Now, a function is a special kind of relation. It's a relation in which each element of the domain is paired with exactly one element of the range. And that might seem a little confusing at first, but let's take a look at some things that are and are not functions and see if we can figure this out. And let's do it by looking at mapping diagrams. As we look at this first relation, we see that each element of the domain is paired exactly with the one across from it. So, by definition, each element of the domain is paired with exactly one element of the range. So yes, this one is a function. When we look at the second mapping diagram, I want you to think, should it be a function or is it not a function? And when we think about that, we really need to look at the domain. How is the domain being paired with stuff in the range? And remember our definition says each element of the domain. So look at each element of the domain. First of all, 1. Is it only being paired with one element of the range? Yes, it is. When we look at 2, is it being paired with exactly one element of the range? Yeah, it is only paired with 5. And the same thing with 3. Even though it's also paired with 5, 3 is only paired with one element of the range. So that means that each of these elements are only being paired with one element of the range. So yes, this is a function. How we get a no is when we get an element of the domain that's being paired with multiple things in the range. Looking at this last mapping diagram, 1 is cool because it's only being paired with 4. So that is just fine. But it's when we get to this 2. 2 is related to 5 and it's related to 6. So now we have one element of the domain being paired with a couple different things in the range, and that's what makes this one not a function. Graphically, it's a little bit easier to tell, and we can do that by using the vertical line test. And the vertical line test is pretty much how it sounds. What you do is you draw a whole bunch of vertical lines. And you ask yourself, does any one of these vertical lines cross my graph in more than one spot? In this case, with our line, we see that our vertical lines only cross in one spot, ever. Right? That means, yes, it is a function. Now the reason for that is that when we draw a vertical line, what we're doing is identifying an x value. So like say this line right here. This thick yellow line is looking at specifically just one element of the domain. And if it crosses our graph in only one spot, that means that it's paired with only one element of the range. Now when we look at the hyperbola and we draw a vertical line way out here. Well, for this element of our domain, it's paired with this element of the range and this one as well. So both the positive and the negative number. And because we have one element of the range being paired with a couple different things in the one element of the domain being paired with a couple things in the range, this one is not a function. So vertical line test says if we get a vertical line that crosses in a couple places, it's not a function. So look at the parabola. Is it a function? Well, it only ever crosses in one spot, so yes, it is a function. Look at the circle. We get our vertical line crossing in a couple of different places, so no, this one is not a function. One way that we haven't talked about representing relations is in terms of equations. Most of the time when you have an equation, it's going to be a function, and it's not all the time. That doesn't always work. But let's start looking at equations in terms of functional notation. And one thing that you might notice right off the bat, like let f of x equal 5x plus 8, how this is set up with functional notation is normally that would say y equals 5x plus 8. But with functional notation, what we do is we name the function. This function's name is f. Right? So function f evaluated at x is equal to 5x plus 8. Now that does not say 5 or f times x is equal to 5x plus 8. That's not what it says at all. What it says is the function, whose name is f, evaluated at x is going to be equal to 5x plus 8. Now that's a great way to define it, because now when we want to find the functional value in relation to a specific element of the domain, like in this case 0, if we want to find out what is 0 really paired with, all we have to do is plug it in. So our function said 5x plus 8. Well, in this case, our x is 0. So we plug 0 in for x. 5 times 0 is 0. 0 plus 8 is 8. So we found the functional value. The functional value is 8. Now what that means is that 0, because it was an x value, is an element of the domain. And 8, because that was the output, the y value, that's going to be the range. And we could also write this as an ordered pair if we wanted to. This would represent the ordered pair 0, 8. So once again, we could see the element of the domain and the element of the range. Let's do it again with g of x. So g evaluated at x would be negative x squared minus 2x plus 7. What's g evaluated at negative 3? So substitute, just plug it in. Wherever you see an x, just put a set of parentheses and plug in negative 3. Don't get lazy and not use those parentheses. It's going to be real important that you do. Because our order of operations says first we have to square that negative 3, which would give us 9, and then take the opposite of it. So this one term is negative 9. And for the second term, we have negative 2 times negative 3, which is positive 6. And the last one is plus 7. So we just add them together. This makes negative 3 plus 7, which is 4. That, once again, if we wanted to think of it as an ordered pair, the x value would be negative 3, and the y value, the functional value, the output, the element of the range, that's going to be 4. Last thing, let's use a table to graph f of x equals 2x minus 1. Now you might already know that 2x minus 1 is going to be a line, you know where the y-intercept is, you know what the slope is, but I really specifically want to use a table to graph this, because we're going to eventually run into functions that are not that easy to graph. And I'm going to ask you over and over again, how do you graph when you don't know how to graph? And the answer to that is to use a table. So what we do is we just set up our table. All right, we're going to pick some elements of the domain and find out what their functional value is. Remember, this is the y-coordinate. So we just pick a bunch of x-coordinates, and for this graph, I'd probably pick like negative 2, negative 1, 0, 1, 2. There's a handful of points. Now, these are just a handful of elements of the domain. Let's find out how they're related to elements of the range. So all you have to do is plug it in. Find f of negative 2. Well, that's 2 times negative 2 minus 1. Negative 4 minus 1. Negative 4 minus 1 is negative 5. Now we find f of negative 1. Plug it in again. 2 times negative 1 minus 1. Negative 2 minus 1 is negative 3. Find f of 0. 2 times 0 minus 1 is 0 minus 1, which is negative 1. F of 1. 2 times 1 minus 1 is 1. And f of 2. 2 times 2 minus 1 is 3. Now we have our elements of the domain being paired with their elements of the range. So really we have a whole bunch of ordered pairs. So we can find those ordered pairs just by basically putting parentheses around here and a comma in between. So that first ordered pair is negative 2, negative 5. So we go back 2 and down 5, which would be about down here. Negative 1, negative 3 is back 1 and down 3. 0, negative 1 is over 0 and down 1. 1, 1 is to the right 1 and up 1. And 2, 3 is to the right 2 and up 3. Now we've just plotted a bunch of points. Do we connect the dots? Well, before we didn't, because we defined the relation or the function as just these specific points. In this case, we just picked a handful of points just to find out if there's a pattern there. Remember that our function is any relation that's going to fit this. So we could pick more points and fill in the gaps if we wanted to. For instance, if we picked 1/2, it would fall right in line with this. If we picked 1.5, it would fall right in line. And eventually, if we picked infinitely many points, they would all fall in line with each other. And so yes, we can draw this line in.